Hello, everyone. Welcome to the eighth lecture. Last week, we talked about a couple of things, but ultimately it all can be summarized that we define this supercumulant expansion for stochastic maps. So to like summarize it, so we have an issue of achieving computability for stochastic map, which when we boil it down to like abstract elements is just a exponent that's modified by time ordering operation, and on top of that an average operation, which in this case was an average over trajectories of a stochastic process, right? And when you take exponent and do such terrible things to it, it becomes difficult to compute it, right? So we had to figure out some way around it. And so to defeat all those difficulties, we invented this by leveraging our mastery over cumulants and time ordering. We invented this supercumulant expansion, which then allowed us to, introduce some perturbation theory, let's say, on this supercumulants that gives us, in the end, a way to compute approximations to this modified exponent. Okay, so again, bottom line is that we had an exponent modified by ordering an average, and we rewrote it as a supercumulant expansion. Okay, so that's the bottom line. I'm like summarizing in this way because supercumulants will return. Okay, it's not just for stochastic maps. So today's topic is finally, I mean, the irony is not lost on me, but this is eighth lecture, and we will be talking finally about open quantum systems. It's the preparations we did for those last 7 lectures will not be won't be in vain. Okay, this was all important stuff that we will learn, couple of techniques that we will implement here sooner or later. But let's get to the task at hand. So dynamics of open quantum systems, so we have to start by defining what we mean by open system. So far we were talking about closed quantum systems, in the sense that we considered a quantum system that is independent of any other quantum system. Okay, I'm underlining that independent of quantum systems because by allowing external fields to influence our system, we implicitly opened it to classical systems, because you can think of external force fields as classical degrees of freedom, let's say. So, but now we want to really take our system and allow it to interact with other systems in the universe, right? So the rules. Okay, so if the quantum system is associated with a Hilbert space, right, with the ket space, operators on this ket space, super operators on those operators, and so on. So we have our system of interest, and you bring in another system, the rest of this universe, let's say. So our system has its Hilbert space. This other systems have their Hilbert space. So now we have to construct a Hilbert space for all of them. And the rule is to take an outer product of those Hilbert spaces. Outer product denoted by a light bulb symbol. Okay. So what in practice, maybe I will name it outer product. Okay, so this is how you do it. So in practice, this means that if B S is a basis in a let's which letter I chose, and would be a basis orthonormal basis in the Hilbert space of our system of interest S, and B E would be an orthonormal basis in the rest of the universe, okay, in this other system we want to bring in, then the basis for the total system SE is created through taking an outer product of basis elements of both subsystems N, J. Okay, so this is what taking outer product means. And now if we have this basis, then we can, decompose this states. State cats in total or composed system. So let's say we have some psi SE. So the superscripts I will use superscripts to indicate, in which system we are. S means our system of interest, E means the rest, SE means both. So if you have basis, this means that you can decompose it in this basis. So you will have some coefficients and J, two indices, because the basis is indexed by two indices, okay? And so it's important, this outer product does not commute, okay? So it's important to keep the cats from the Hilbert space of system S are on the left here, the others are on the right, and you have to keep this in, you have to keep this straight. So that would be some state psi. You take some different states phi, again, decomposition. We'll have some coefficients here. You probably know all this stuff, but just to make sure that no one is lost. If you have states, you can calculate inner product. Let's say between psi and phi. This again, and J and prime J prime. We have our coefficients and J phi n prime J prime. We take brass corresponding to cats, right? And cats of the other vector, right? And this, the inner product, there is a name for this property when you distribute it over the inner product and the outer product. They are, I forgot the name for this property. But to evaluate this, you simply go N prime times NJ prime, okay? So this is the rule, how you evaluate inner products of composed Hilbert spaces. And these guys, we know what they are. This is just delta and Mn prime. This is delta J prime, because orthonormal basis. And you get what you would probably expected, and J and the. Okay, same, we have in a product, we also have operators, of course. Operators, so if I take an operator SE just to indicate that it's it acts on the total Hilbert space, you can of course use for it the standard approach. J, there is some matrix element, prime J prime, and prime J prime, which again can be further simplified. Can write it as outer product of cat brass. Okay. Yeah. So if you have this form acting with an operator on cats, it's fairly straightforward. J prime prime. So that's an operator, right? And that will be the cat and bis J bis and bis times J bis. And it's simplicity itself. And J and prime J prime and bis J bis coefficients bis J bis. And this, what's happening here? Well, N cat bra meets N bis light bulb J prime meets J bis. Okay. And of course, this is something we know how to handle. This is delta J prime J bis. And you get again something it's probably you would expect. And J prime prime. Psi J prime prime. And when operator acts on cat, you get cat in return, right? All right. So these are the rules, okay, for anyone who haven't seen this before. Now might be a little bit more interesting stuff. So we know how to write down operators, of course, density matrices, density matrix of total system. It's just yet another operator. So of course, density matrix is something. Just treat it as any other operator. And J prime. And we have states, so we have expectation values of observables, X expectation value of observable. It's again standard rules. So an expectation value of some observable belonging to the total system. Belonging to the total system, that is, its operator is an operator in the composite Hilbert space, and it's you have to take trace just to trace over whole space, an operator acting on density matrix, right? Which it's what trace would mean here. Just pick basis SE row SE and calculate this sum over diagonal terms. Yes, thank you. So that's just, this is the formula, standard stuff. And now interesting things will happen, because so far we just took two systems and just merged them together so that we just have another system that's just bigger. Okay, but now the interesting stuff starts to happen. Okay, so among all the possible observables, there is a class of observables that belong only to one of the subsystems. Even though we have a big system SE, we can isolate the observables that just belong to just S, for example. And such observables, so I will call them S only observable. Those guys, they will be represented by an operator of this form, okay? So it is an operator that acts on ket space of S, of system S, times identity in the subsystem of the rest of the universe, okay? So it's, in the sense, it's like independent of, it's not independent of E, it does not affect E, okay? This operator doesn't affect what happens in E. It's like neutral in this sense for E. And now if you want to calculate its expectation value, right? So there will, couple of things will happen. If it's of course trace, total trace times 1 row SE, okay? And it's again, you sum over, you take the diagonal terms, J, AS times 1 times row SE, and J. And the interesting thing happens that if we look here, okay, this bra J, it will just slide through the observable, okay, because there is identity here. It just slides through. So what we are getting here is like the sum over N. So you get this, you get operator S, and J, so off-centered, and J row SE, J okay, you get something like this. So this looks like a, this is so ugly. I'm sorry. Let me write it again. Row SE. Okay. So this thing looks like if we taken a trace, but only over the basis elements of the E subspace. Okay. So it looks like not a complete trace, but a partial trace, okay, as it is called. So, and then what is left, okay, this looks like the trace over the what's left that is over S. So what's happening here? You have trace over S. It's the S part of the observable, the one that's not trivial. And here we have something that's like trace over E of the total density matrix. All right. So this trace over E, so let's focus on this guy for a bit. Let's call it rho S, and it trace over E, rho S E. So you just evaluate this guy, this bad boy. You get the sum over J, rho N J, N prime J. So it's like diagonal parts, but only in this E part. And you are left with ket bra, but only in S. So after taking this trace, you are reducing the total density matrix to the operator that operates now only in S subspace, okay? And moreover, you can check this from some simple algebra that this rho S is, it has trace one, and it's positive semi-definite, okay? So in other words, and it's Hermitian, and positive semi-definite implies that it's Hermitian. So in other words, this rho S, this partially traced density matrix, can serve as a density matrix in subsystem S, okay? So this guy, this rho S, it's called, we call this either reduced density matrix, or just simply state of S, of subsystem S, okay? So whatever floats your boat, because this rho S partial, which is obtained from the total state, is a proper density matrix, therefore it can serve as a state. And moreover, when you look at the expectation value of S only observable, you can see that you get the formula, you get the standard expression, right? It's a trace over space of operator representing the observable times the state of the system, which rho S, therefore rho S really acts as a state of the system S, even though we started from the total system that is larger by addition of this S E subsystem. So the special case when uncorrelated state. So when there is a special case that the total density matrix of our system is actually product of two density matrices, okay? Now, we call this an uncorrelated state, and it has this funny property, okay? It's this straightforward property that when you take partial trace over E, so you want to reduce your total state to a state in subsystem S only, this is it's it's extremely simple. This is density matrix, so is equals 1. So essentially, there is no reduction, let's say, in any information when you trace over E when states are uncorrelated. In other words, if I calculate the expectation value of some S only observable with uncorrelated state like this, okay, it behaves as if subsystem E did not exist, okay? Because I can this is exactly the same as just taking, I can just multiply it by 1, then I can just, 1 I can express as a trace of the E density matrix, okay? And then I can extend my trace to be over total space by adding identity for my observable and by multiplying. Okay, so if the state is the state is uncorrelated, then from the point of view of observables in belonging to subsystem S only, the system E could not exist at all. Okay, that's what I'm trying to say. So uncorrelated state. So we call it uncorrelated because it implies that the systems S and E don't talk to each other; they're independent of each other. So if this is the case, you can simply forget about E, and this is how you can actually arrive at the notion of isolated systems. Okay. However, when they are not uncorrelated, when S and E are correlated, are dependent on each other, but we still focus, if you focus on S only observables, and S, E are not independent. So are not independent. So the state cannot be written as a product, it's an uncorrelated product. Then we say that system S is open system. S is open system. And it is customary to call the rest E as the environment. The environment of S. All right. So we focus on S only observables, which means that to calculate their expectation values, we need to have an access to the reduced state of S. Okay, which because S and E are not. Sorry, give me a second to just close the door. Okay, so we focus only on S observables. So to calculate their expectation values, we need reduced states of S, right? So we take the total state and take its partial trace. But since the S and E are not independent, this partial trace actually does something non-trivial, okay? And if this is the case, then we are talking about S as an open system that is open to its environment E, okay? And this some interactions with environment will have some non-trivial consequences for the dynamics of states, of reduced states of S, okay, which we need to calculate expectation values of S-only observables. So that is the setup. That is basically a long-winded definition of open systems. And now we know what they are. Now we can proceed to talking about exactly the dynamics of such systems. So 4.2, dynamical maps. All right, so if you are interested in describing open systems, right, the basic thing we have to figure out is how to describe their dynamics, okay? How they change in time due to interactions between them and all other things present in the system. And well, the most, let's say, straightforward approach would be to simply, okay, so let's start with Hamiltonian. Maybe let's call it simplest approach. One. Take the total Hamiltonian. Total Hamiltonian, which I will denote as HSE, right? SE because it's for the composite system. And such Hamiltonian can always be written in this following form. So 1 times HE plus some constant lambda and the sum over indices alpha belonging to some set S alpha E alpha. Okay, you can always, any Hamiltonian in the total space, so when Hermitian operator in the SE Hilbert space can be decomposed into this form. So here you can read out that this part, it describes the Hamiltonian. So no, this part would describe the dynamics in S and E if they were independent. Okay, if they just never talk to each other. This part is an interaction part, and this is what causes system S and E to not be independent. Okay. So take the simplest approach. You take the Hamiltonian. You can decompose it like that if you wish. Next, just compute the total unitary map. Right, so we just take U as E T0, which would be just exponent minus I T commutator with Hamiltonian. So I write this like a outer product of bullets just to underline that this is a super operator on the whole SE, the space of SE operators. Okay. Then in third step, just evolve the initial state. Right? So we just calculate SE T by applying unitary map, the total unitary map to the initial state, okay? And 4, compute the partial trace over environment, right? Rho ST would be then just trace E rho SET, which you can write as trace over E, unitary map acting on the initial state. And that would be say, the most straightforward brute force approach. So, you know, if we are here, let me already point you to some assignments for you to figure, for you to look at. So we are here, okay? We have the Hamiltonian, this form of Hamiltonian. So we have here like 3 assignments, 26, 27, 28 for you to check out. So the first one, the 26, is to show that indeed any system environment Hamiltonian like this can be actually written in this specific form. Okay, so check out how you arrive at that. It's good to know this. Then the 27, assignment 27 is to show this identity, okay, that when you take a unitary map for a Hamiltonian, SE Hamiltonian, where there is no interaction, you get this like simple factorization for independent unitary maps on S and E. And finally, assignment 26, take this brute force approach I just sketched for you and apply it to a very simple problem where the open system S is actually a qubit, okay, the simplest quantum system possible, and its environment E is actually also a single qubit. So you have 2 qubits interacting with each other through this Hamiltonian, so sigma Z times sigma Z, and we want to treat one of those qubits as an open system and the other qubit as its environment with this initial state. So check out those calculations and to see how the brute force approach works in practice. Coming back to the matter at hand. So of course, this program of just treating this total system as just another basically closed system, calculating a full unitary map to get the full evolution of everything at the same time, then just propagating the initial state, and at the very end, just going through motions of computing a partial trace. This brute force approach, of course, have any chances of working, provided that S and E are extremely simple systems, like those 2 qubits from the last assignment. Okay, you can imagine that making the distinction between open system and its environment does not really make much sense if S and E are extremely simple systems, like 2 qubits or even 4 qubits, whatever. The isolating S as in like the system of interest and E as the rest, the scary rest of the universe, the environment. Well, you do it in situations when environments is so complex that it's completely unfeasible to compute a full unitary map for the system E or system S plus E as a whole, or even in the cases when you cannot even fully characterize what E actually is. right? Maybe you have some partial information about this Hamiltonian, maybe you don't have the full picture, but all in all, you make the distinction between the system and its environment only when its environment is so complicated that this brute force approach have no chances of working. Okay, so in other words, the very nature of the problem of open system dynamics is such that this whole program just goes to trash. Okay, we have to figure out something completely different. And the most natural way of thinking about this problem then, if not this, the most natural way of thinking is to like rephrase it in terms of what I call the dynamical maps. Dynamical maps. It's my approach. So the idea is that we want to define a super operator that essentially takes the initial state of the system, of the open system, which would be a reduced initial state of the total system, and just transforms it, dynamical map, into a state of the system at later time t, which by definition should be equal to the reduced total state at time t. Okay. So in other words, we would like to have an operator, a super operator D, such that rho as t equals super operator acting on the initial reduced state. Okay. So then this D this would be the dynamical map we are looking for. But now, when you phrase the problem in this way, you're making this implicit assumption that you're making this implicit assumption that this super operator D will play here the same role as the unitary maps or stochastic maps in scenarios we considered previously. So what I mean by that is that this D, this dynamical map, on the one hand, we want it to contain encapsulate all the dynamical laws governing the dynamics of the system S, influenced by the interactions with its environment E. But on the other hand, this dynamical map, it has to be independent of the initial state of the system, right? That's why we want to write it as D acting on rho S. Okay, so the idea is that this dynamical map, you can apply it to whatever initial state of the system, and it will evolve it according to according to the same set of rules. All right, and this is how we tend to think about dynamics in closed systems as well, right? Because if you have your system, you think of your system, you don't identify it with any particular state, right? Initial state is just a hat, let's say, the system can wear. Its true essence, true identity is what are its dynamical laws, right? The Hamiltonian or the unitary map that's generated by the Hamiltonian, right? This is what identifies the system. Initial states are just options, settings that you can give the system, and if you change initial state to something different, you don't say, oh, I all of a sudden change my state, my system to something else. No, it's just still the same system, just in different initial condition, because the dynamical laws represented by the unitary map are still the same. Okay, and this is what identifies the system. This is its essence. Okay, this is its descriptor. Okay, and we want to have the same thing for open systems, right? We want to have something that characterizes its dynamical laws, so that the initial states can be like, the options we can choose for initial conditions, essentially. So that would be a dream. This is what this evolution map approach implies. But here is an issue, because while it is very simple to like isolate the Hamiltonian, the unitary map from the initial state in closed systems, in open systems there is a caveat here. Okay, there is asterisk, because as it turns out, it's not always possible to define such a initial state independent map. Okay, not for every initial state rho SE. Okay, not always possible to abstract dynamics from initial condition. Okay, so this is problem. It's a problem we face. So to show what it means in practice, let's just take some arbitrary initial total initial density matrix, and let's decompose it into like two pieces. So we will essentially take rho S and add and subtract a product of operators. So let's add partial trace over E rho SE times partial trace over S. So we are taking a product of reduced states of S and reduced states of E, right, symmetrically. And on the other hand, we subtract the same factor, the same term. 3 plus E. And now once we done this, so this here we recognize that this would be rho S 0. So this by analogy would be like rho E of 0. So we have here a product of reduced states plus the remainder. And the remainder, I would just call it a correlation. Okay, the index quad to indicate correlation. So in other words, I mean, I just added and subtracted a factor. Okay, I can always do that. So in other words, if my initial state is simply uncorrelated state, so it is a product state, this correlation part is just 0, disappears. Okay, so if it's not that, cannot be written as a product, then this thing is non-zero. All right, so this is like what quantifies, in some sense, quantifies correlations between the initial correlations between system and the environment. Although having this definition, you can notice that if you take a partial trace over E of this correlation part, it actually disappears. Okay. So this is just the consequence of this simplistic definition. And now Okay, so this would be we made this decomposition, and now let's check out the state of S, so reduced state at time t. Okay, so according to our definition, this is just reduced total state at time e. Okay, which is a total unitary map acting on the initial state, right? And everything is traced. And now we can put in our decomposition. So we will get here rho SE T0, rho S 0 times rho E 0, okay, plus the part that contains the correlation SE core. All right. And now here we can treat this thing here, okay, as a super operator acting on the initial state of S, all right, plus the remainder. So this is what I was talking about, okay? So we have here a transformation that pushes forward in time initial state that is independent of the initial state of S, right? Because we want to have a dynamical law for the open system itself, okay? So it can be dependent on the initial state in E. We don't care about that. We want to have it abstracted from the initial states of S only, okay? So this part is what we are looking for. This could serve as a dynamical map we have in mind. But the problem is that we have this guy here. And it is true that trace over E of the correlation part itself disappears. But once you transform it with the evolution operator, super operator, this is in general, it's not zero, okay? It's something. And it's also, it does depend on the initial state of S, right? Because it's I mean, you can see that it depends explicitly on the initial state. So in other words, in general case, if someone emails us a initial state of the total system, it will be impossible to define this dynamical map that is abstracted from the initial state. It will be just, well, the best we will be able to say is just some correspondence between initial state and the state at time t, but there won't be this, this dynamical laws for the system itself. Okay, it will be dependent on the initial state. This is something we really don't want to see. We don't want to, live with this kind of formulation. So this is a problem, right? So what is the solution? Well, unfortunately, if you want to be safe and never bother with this part, okay, the only real way to do it is to simply assume that this correlation part is always zero. In other words, if we assume that the initial state is always in the product form only, okay? So the initial state of S and E is always uncorrelated, we can have our dynamical map. And it is the only way to make sure, all right? And this is the standard approach. If you want to have the formulation in terms of dynamical maps, which quantify the dynamical laws of the system, of the open system S, the only way to achieve this is to operate under assumption that the initial state of the total system is a non-correlated one. So always assume that rho SE0 is a product. And from this point on, this is what we'll always do. Okay, the silent assumption is that the initial state, the state at time t equals 0, is a product. Okay, and this is the only way to proceed in this fashion. Okay, there is some. Okay, it's not like there is nothing in the literature about the case when this assumption is not made. Okay, people explored options for creating some kind of theory or some formalism for handling initially correlated states. But it's, as far as I know, there is like no one came up with like a general purpose theory that would work for any initial state. Okay, if you want to have something that shapes into a theory of open systems, you have to work under this assumption. Okay, nobody came up with something like that generalizes this, and this might seem super restrictive and perhaps is a big no-no. Okay, maybe it makes this whole theory completely trivial and useless. Well, it might seem like that, but if you think about this, if you make this, you think about the conditions under which the systems which you want to describe using this kind of theory. All right. So typically, if you are making this distinction, complicated environment that is like beyond your control, there's something, heat bath, whatever, something, some noise, electromagnetic field from outside the building, some complete nightmare, the rest of the universe, essentially. You have no influence over it whatsoever. It's just there, but it seeps into your experimental system, and you have to include some interactions with this monstrous rest of the universe. But on the other hand, the system S, the one you are interested in, is something you are controlling quite well. It's a qubit in your ion trap or whatever, or something like that. Something that you have control over. Something you can make experiments. Something for which you want to measure observables belonging only to this subsystem. Okay, but if you want to do measurements, experiments, and stuff like that, you want to measure as only observables. Well, to do that, you have to be able to initialize your system in some controllable way. All right. So each of your, so if you are thinking of this kind of setup, you will be any experiments involving this setup will involve you initializing S in some specific state. Okay. But only S, because you have no control over E. It does its thing. Okay. So if you think about it in this way, then when you say initialize S in some specific state, this automatically implies that you are producing this kind of product form of the initial state, right? Because you're setting up something on the S side that you start something it's all environment and your qubit interact with each other for some time, so they are correlated. Some monstrous thing is happening, but now you come in, you initialize the experiment, you set state of S to something specific, and this automatically implies that you severed all the correlations with E. All right. And then you run your experiment when the S and E become correlated again, but the starting point is something you purposefully initialize in some very specific state. So in other words, it sounds restrictive, but if you consider in what kind of experimental scenarios you would use this theory, it all of a sudden it's not so restrictive, because vast majority of those kind of experiments will want to start in this kind of initial state, right? So it sounds restrictive, but if you think about it, it's actually the only game in town, all right? So that's why it makes sense to proceed further. Okay, it's not assuming this product form doesn't make the whole theory, the whole following theory, completely useless. It's still very much useful, and actually in most of its use cases, this is what you would get anyway. All right, so I whistled my way out of this problem. So I propose to make a 5, maybe 10 minutes break uh, before we proceed further. Okay, so 10 minutes, 10 minutes break. All right, nice. Okay, so we can proceed. Yeah, so the next thing is a oh, it's super cumulant expansion again. Yeah, exactly. Because so if we work under this assumption, right? So then our dynamical map. So we have our dynamical map then. Okay, so this is like this super operator then that acts on density matrices in S subspace uh, system Hilbert space. Okay, uh, and it's by definition is a you take the total Hamiltonian, total unitary map. You take the initial state of the environment, and you take partial trace of it. Okay, so that would be our dynamical map. So the next step would be, okay, so how to actually compute this beast, right? Since we cannot compute this USE. So what chances we have to actually compute this more complicated expression? So before we get to that, let me settle on some notational conventions, okay? Because we have to pick our symbols to proceed further. So let me do some notation. Some notation. So I start with, so we have our total Hamiltonian, right? This is always this is where physics comes in. And we have this decomposition in like free part. What would happen if S and E never interacted, plus the interaction term, which can be written as this sum, this of product operators. Okay, so these are explicitly operators that act in S and E subspaces. And as it turns out, there is it won't be apparent immediately, but there is an advantage to shift the interaction operators by their average value. Okay, so let me do some transformations. So what I mean by shifting, I want to add here I will explain the symbol in a second. But this is a number, okay? A number times identity, and subtract the same. Okay, so I didn't nothing changed. Okay, I added 0. But now I want to rearrange some stuff here. So for one, let me collect all the terms. Oh, you know what? Let me add here subscript 0. This is like a bare Hamiltonian, bare-free Hamiltonian. Let me collect all the terms that are multiplied by identity on the right side. So this is, of course, the bare Hamiltonian is here, but also we have term here. So I will get 1 sum over alpha.
As 0, 1. Oh, okay.
How if
It includes both parts from S and from E. So that we call S.
this is a bare, this is only S, okay? The bare Hamiltonian.
As well. I see, we're being like that. Okay.
Yeah, then we will change it a bit. And S alpha, okay. So I want to collect those guys on one side, plus the environment Hamiltonian, I leave it as it is. And the coupling, I leave the subtracted part in the coupling. This is just some mysterious adding zeros, juggling of terms, okay? So far it's completely unclear what's going on here, right? And now, so let me call this. So this is bare Hamiltonian. So let me define a shifted Hamiltonian, which now depends on, because this thing will depend on time. Alpha S alpha times F. So instead of the shift, E alpha is one of the bare interaction, environment side interaction operators. F will be the shifted version. And it also now depends on T. Okay, so that's just some, I juggled some terms. And now what is this average value? So this is, let's call it average value of E alpha. So this will be, by definition, trace, well, over E because it's E I H E T E alpha. So this is the interaction picture of operator E. And because it's this is environment only operator, so its interaction picture is defined with respect to the free Hamiltonian of environment and the environment initial state. This is what I want this average value to be, okay? And I can do some juggling of terms here, use the cyclic property of trace to rewrite it in different way. If I move this part, this evolution operator, I use cyclic property to move it here, okay? I will get E H E T rho E0 E I H E T. Okay, so that's simple stuff. But this thing is if you recall, this is the same as taking super operator generated by the Hamiltonian acting on rho e, all right? Which we can customarily call it as a unitary map, but with index e, okay? This is just to introduce some notation. So this thing is this average value explicitly depends on time. Therefore, when I do this juggling, this new system Hamiltonian is formally depends on t, and this shifted coupling also depends on t. But it will, believe me, if we don't do this now, we will have to do it later, because this is just the benefits are big, although completely not apparent at the moment. The other notation convention, so this thing will appear over and over and over again, okay? And it's too many symbols to write, right? So I will, so this sum alpha S alpha times f alpha of t, let me just write it as kind of scalar product, all right? Okay? We won't be using it very often, so just for the purpose of this last hour here, maybe next lecture also. But this will just save a lot of time and effort in writing down. So this symbol. So this maybe I could write arrows also, but this is just this, okay? This is just a shorthand for this whole sum. And finally, let me switch to the interaction picture. So this is our dynamical map. So this thing here is generated by the total Hamiltonian, right? So I want to switch to interaction picture where I will disentangle the free evolution, the independent evolution part, okay? So we can just focus on the interaction between S and E. So switch to the interaction picture. We are always doing that, right? With stochastic maps, we also did this. So we have our trace E over E with the full Hamiltonian, right? This is our starting point. And it acts in Buller plus initial state. And now I want to disentangle the free part. So I will get T over HS. I need time ordering because, you know, formally this dressed shifted Hamiltonian is now depends on time, right? So we have to respect this. HS du bullet du times the environment part is it's constant. The Hamiltonian of environment is constant. So one of the assignments is I showed you previously is to show that if your generator is of this form, so h times 1 plus 1 times h, right? The exponents will factorize in this. Okay, so this is one of the assignments you can use to show this. And the rest, so we disentangled the independent part. So we are left with dependent part. with interaction part, sorry. 1I lambda, so the coupling integral as scalar product with f, index u, du, and the density matrices, 0 close partial trace. So this is interaction picture. So this guy here, we called it U E T0. Okay, so then by analogy, we can call this S US T0. Okay. Interaction peak of coupling. So the thing here, this is a coupling and it's interaction picture because we disentangled one part, so we have to pay for it by switching to interaction picture here as well. And it's a standard, the definition is standard. So it's a US 0. No, let me use T here because I will just argument T. It will be cleaner that way. UE0 T S times F. Well, formally depends on time. And you multiply it from the other side. Evolution operators. E. So this is the standard formula, and we can rewrite it completely in the super operator way by doing this. So this is the interaction picture of the coupling. And this is the standard formulas that we derived in like lecture 3 or 4. I don't remember exactly which one. So this is what stands here. And now everything is under the trace over E, which means one, the S part, we can just bring it outside the trace because it's not affected by trace over environment, obviously, because it's a S only super operator. So we'll be left with this part under the trace, right? But this super operator, like we had it wait a minute. Yeah, okay. So sorry, I had a I had a brain fart for a second. So let me continue. So let's extract the S part, okay? And we are left with trace, and we will have, if we write this guy as a sandwich, where is it? Oh, okay, here, this is the same as taking the sandwich, right? But here we have the sandwich means that it's minus I THE. Here we have our SF, the interaction part, right? Q U bullet times rho E0 EITH E. Okay. So we have the whole thing sandwiched by unitary operators, and it's under the trace. So I can move this guy over here, where it will cancel, right? I move it here, so then it's EITH multiplies E minus ITH, okay? So this is like a general thing that always happens, okay? When you switch to interaction picture, you have trace or partial trace, the free unitary maps, if they are under trace, they will just cancel automatically, okay? So in other words, we are left with S part, E part, S time F. Symbolically write it like this: lambda 0 T, interaction picture of the coupling, U du, acting on rho E0 trace. Oh. And I will call this guy, this will be our dynamical map we are interested in, and I will use for it a notation like this. Okay, so it's like stochastic map was U with bar, and this will be U with angle brackets, because this partial trace over E with this initial state here, it kinda looks like an average. Kinda sorta looks like an average. At least like intuitively, it seems to be something that's like maybe it's analogous to what we dealt with previously with stochastic averages. If not in form, maybe in function. Like it reduces the environmental degrees of freedom. It like modifies the time-ordered exponent. It kind of looks like an average, right? That's why I call this the shifted thing, average value, right? Because this is like the same kind of deal here. It's kind of looks like an average. So I pick this kind of notation for this dynamical map. And now the issue is the following, right? We know from our previous experiences that if you have an exponent that's modified by time ordering, that's difficult, but dynamical equation allows you to solve it usually. But then if you add on top of it another modification in form of some kind of average operation, stochastic average previously, that makes it very difficult to compute, right? So, but nevertheless, we came up with a method to fight on this, right? The supercumulant expansion. So here again, we have a map exponent, there is time ordering, and there is this additional operation, additional modification. It's kind of like average. This, of course, make it difficult. I mean, there is no dynamical equation for this super operator for free, as you can probably predict that it won't be that easy. So it's difficult to compute, right? And it is actually a notoriously difficult. The dynamical maps are notoriously difficult problem to tackle. It's much more difficult than stochastic maps. It's more complicated, more moving parts, as you can see. There's operators everywhere, partial traces. It's much more weirder than some just averaging with probability distributions. But nevertheless, we can, if this partial trace, we think of it as an average, and even if this notion is not completely strict, nothing stop us from trying out supercumulant expansion. Okay, it worked very nicely for stochastic maps where there was a real average there. Maybe it will also work for this weird quantum average, if it's even worth calling average. I mean, nothing can stop us for just postulate super cumulant expansion. Nothing stop us from just taking this this dynamical map, which is again trace, time ordering, SF, blah, blah, blah. I don't want to write it again. It's here, okay? And we say, okay, let it be another exponent, time ordering, over superoperators L. This will be a supercumulans, but quantum supercumulans, so different letter than before. Exponent, sum, n from 1 to infinity, minus I lambda n integral T L n u0 du. So this is the same kind of form, same kind of implicit definition as we used previously, and nothing stops us from saying this. The question is this implicit definition actually well formed? Will it allow us to obtain the explicit values of supercumulans L? And the answer is yes. Okay, so this actually works. And the technique, the standard technique, you expand the left-hand side in a power series in lambdas. You expand the right-hand side in the power series in parameters lambda, compare the terms, and you will get a whole infinite set of equations, and you check if you can solve them. And proceeding from the lowest order, from lambda 1 order, and so on, we will find that, again, just like with stochastic maps, we will be able to solve each equation like iteratively. Okay? And to maybe demonstrate it, what do you get? So I have here as an assignment, but you know what? Maybe let me switch to PDF. So I don't want to overburden with assignments. Right. So the assignment is to find the explicit form of fourth supercumulant, which means that you have to take a left-hand side, expand it, right-hand side, expand it, and start comparing terms of same order in lambda. And I wrote down here what you get when you do the expansions. Okay, so just to show how it works more or less, and why it actually gives us the answers, gives us solvable equations. So I took the dynamical map, so the left-hand side, which is time-ordered exponent, right? You recognize all this stuff, and it's partial trace over E. So when you expand it, the zero order in lambda is trivial, it's just identity. The first order is, you can find it quite easily. It's just this kind of superoperator, and you cut off the higher orders. And on the other hand, you take your supercumulant expansion, expand it, isolate the lambda 1 order, and you get that this is just integrated L1. Now you compare them, and easily you can see that this means that L1 is fully expressed by known superoperator from the left-hand side, right? Which you can calculate it to how far you want to push the partial trace. You can obtain different forms, but the key point, and this is why we did the shifting in the beginning, you get that this L1, it's proportional to the trace over coupling F, okay, the average of coupling F. But by shifting by the average value, we make sure that this is zero, okay? So F is like the coupling that has zero average, okay? We made sure that it's like that, which means that L1 is zero, okay? So we start from the second order. And again, you do the expansion. On the right-hand side, you also do the expansion. L1 appears, but it's zero, so you can just forget about it. You get L2 on the right-hand side. Left-hand side, you have some super operators. This is a solvable equation. You can push it however you want, and you can continue on, and it will always lead to something that's you can find any order of L of supercumulant. You can solve it up to any order, provided that you solve all the previous orders. So this is, if you have enough patience and time, you can calculate whatever L you want. So this is like, it works, again, it works like it works with stochastic maps. So check out the assignment 30 if you want to look again on those calculations. But now, before we finish, so our short-term goal was to define dynamical map, right? And we got this. We had to assume the initial condition was this on that form, and we got our dynamical map, right? It's here. It's this beast. So now the problem is, okay, how to compute it? This is always the problem, right? So short-term goal was to figure out how to do it, how to do the computation. And by looking at it and thinking, oh, it looks like it's average, kind of average, let's try supercumulant expansion. The supercumulant expansion actually works. So if it works, then we can build a perturbation theory around this expansion, which we discussed a little bit before. So in this sense, if you just look at it from purely utilitarian point of view, we achieved our goal. We have a computability of dynamical map. However, we are not just some robots here. We are physicists, goddammit. And the fact that this supercumulant expansion actually worked, it only reinforces this idea that this partial trace actually is like an average. So this analogy is not just a vibes, maybe. Maybe it's not just accident that it worked, but maybe there's something underneath, okay? And as theoretical physicists, we are obliged to try to explain it before we say, oh, it's just coincidence, okay? We want to do it. We want to try to explain what's going on here. And to find this, to formulate an explanation or to try to put a meat on the bones of this loose idea that this kind of looks like an average. If it is an average, then we have to answer two fundamental questions. One, if this analogy really works, then we have to identify what is a distribution we are supposedly averaging over when we calculate this partial trace. And two, if we manage to find this distribution, what is the nature of variables this distribution distributes? With stochastic maps, the variables were trajectories of a process, right? And the distribution was a probability distribution on the space of those trajectories, right? Is there the analogous entity in case of quantum, this quantum average. And before we jump into discussing computability and perturbation theory based on cumulant expansions, we will make an excursion to figure out what's going on with this quantum average. Is it really an average? And if it is, what is the thing we are averaging over actually? What is this thing? Is this like stochastic process? Is it different? And this is what we'll do on the next week.